Okay, so in the first case study of this dimensional analysis section, we looked at estimating the yield of atomic weapons from a picture of an explosion that was taken back in the 40s, right? And that's actually a very famous example that comes up a lot in physics classes for using these kind of dimensional analysis and estimation techniques to get a handle on, rough order of magnitude estimates. But this class is really, I think, about seeing the physics and the quantitative nature of things in the everyday world around us. And so I want to go through a very different case study of using the same kinds of ideas in a little bit of a more prosaic setting. So here is a stock image that I found where someone took a photograph out of a train window on a rainy day. I'm sure we've seen things like this in our everyday life where, it's raining, so there's droplets of water on the window, and as the train speeds in some direction, those droplets form like these diagonal tracks across the window pane. And actually, they all kind of seem to be going in like a vaguely similar way. Something interesting is happening up here where it's like, maybe as the droplet maybe bumps into another droplet, combines and becomes bigger, it looks like this angle, this trajectory changes a little bit. But for the most part, you've got things that are kind of going on this diagonal slant. And I want to ask, can we use these same kind of ideas of dimensional analysis to estimate, well, if I observe the angle that these drops are moving across my window at, can I figure out or can I estimate how fast this vehicle has to be going, right? What is the relationship between the speed of the train in this case and the angle that these droplets make, right? And a priori, just from first principles, the answer to this has to depend on all kinds of complicated things, right? You've got a blob of water with the molecules adhering at some strength to a piece of glass, or maybe it's a piece of plastic. Does that matter? You've got, air whooshing past it, kind of trying to force it backwards. You've got gravity pulling down. Like, what goes into determining the precise, magnitude of, say, the force of drag on a rain droplet, so on and so forth. Again, if you want to know precisely the answer, you have to do a hard calculation. But if you just want to understand the kind of relationship between, well, how does the droplet trajectory change as the speed of the train changes, or as the size of the droplet changes? For that, again, dimensional analysis can tell us basically everything that we need to know. So I've kind of zoomed in on this part of the picture here, and I'm going to focus on this little drop. And I've drawn a schematic cartoon. These are often called free body diagrams, and we'll be seeing them, if you haven't seen them in previous classes, we'll be seeing them more, and I'll go into a lot more detail about this later on in the class. But I just want to give you, again, kind of a feeling for the logic of the approach that we're going to take. It turns out this is actually a harder example, a harder estimation in one very important way than the first case study we did. So don't worry if you don't understand every detail of what I'm walking through, but again, try to appreciate the general strategy of thinking about dimensions of different physical quantities, realizing that dimensions of different quantities in an equation have to match, and then thinking about what the dependencies of some of the things that appear in these quantities has to be, and then making progress from there. Okay, so I've drawn this free body diagram, and I've said, okay, well, here's a cartoon of a raindrop, and on the one hand, the train is moving at some speed off in this direction. The droplet, as it moves across the window, is also going at some speed, and it's making some angle, across the window pane, which I've drawn with this little cartoon and a theta here. Right? What are the forces that this droplet is experiencing? Well, on the one hand, gravity is always trying to pull it down. Right? So that's one force. On the other hand, the air kind of whooshing past it has this drag force associated with it, and it's trying to push it. If the train is moving this way, then the force, I guess I should match colors. If the train is moving this way, then the force of drag is moving exactly opposite. Right? And then, of course, there's this adhesion force, the fact that the droplet is sticking to the window, and it's almost like a friction force. So this adhesion kind of points in exactly the opposite direction as the velocity of the droplet. It's just trying to slow the droplet down from moving, right? So if the droplet was perfectly at rest, it would be adhering, but it wouldn't be resisting any motion, right? Other than gravity, I suppose, right? So what we want to understand in this case study is to say, what is the relationship? What is the relationship between the speed of the train, which I'll just call v from now on, between v and this angle theta? So if I just watch the direction that a droplet is moving, can I figure out how fast the train is going? That kind of thing, right? So what do we do? Well, we've got these 5 basic quantities that have to be contributing, and we can start eliminating things that we don't need to focus on right away, right? So first, let's focus on, what do we know about what determines this angle, right? So the force of adhesion, this kind of frictional force opposing the motion of the drop as it kind of moves and fits and starts diagonally across the window, that just tries to slow the droplet down. It doesn't actually choose the direction that the droplet is moving. So we can actually, for the purposes of this estimation, ignore the precise details of this, right? And so then you can say, well, the velocity of the drop, the direction of the velocity of the drop, is just going to be set by the actual forces the drop is experiencing. And the only force the drop is experiencing is both the force of gravity and this drag force. The speed of the train matters, but as we'll discuss in just a second, it only matters in setting what this drag force is, like how big that force is. Okay, so if this angle just depends on, the relative magnitude, this competition between gravity and the drag force, we can use our basic, geometrical understanding to say that the tangent of this angle, tan theta, right, is like opposite over adjacent. That has to be set by the ratio of the force of gravity to this drag force. Okay. So that's great. We've already simplified our problem and said, the angle depends on this ratio, and we'll have to do some dimensional analysis to figure out how the details of this ratio depend on the thing we're trying to connect to, right? But let's see how far we can get first. Well, first, the force of gravity, as we'll see repeatedly in this class quite soon, this one's easy, right? And if you're near the Earth's surface, the force of gravity can basically just be written as, well, what is the mass of the object? So what's the mass of the raindrop? Times this quantity g, the acceleration due to gravity. And just so that we know, g is approximately 9.8, sorry for a little bit of computer lag there, 9.81 meters per second squared. So near the surface of the Earth, it's basically a constant that tells you what is the acceleration due to the presence of the Earth, right? For a relatively light body near the surface of the Earth. Okay, so great. Force of gravity, that's something that we either already know from high school physics or will soon remember or soon learn from a future edition of this class, future lecture of this class. And then what we really need to do, though, is estimate this drag force. Okay, and that's where we're going to turn back to these ideas of dimensional analysis to ask ourselves, what could the force of drag possibly depend on, right? So what must F drag depend on? Okay, so this is, again, where we put in our physical understanding of the world to help us answer this question, right? So, okay, we've got in our mind a picture of a droplet of water with air, moving past it really quickly. So how much force is being applied to that drop by those processes? It seems pretty clear that the bigger the drop is, the more force it will feel, right? Because you've got air molecules whooshing past it over a bigger surface area, right? So probably the droplet radius, r, and as we've seen already, the dimensions of a length, that's just a length. Okay, it better depend on the speed of the train, otherwise this whole exercise is not going to work. But of course that also makes sense, right? The speed of the train sets how fast air is, moving past the droplet, even in the absence of wind. So the train velocity surely matters, train velocity v, and the dimensions of the train velocity, well, that's just length divided by time. So I'll write that as length times time to the minus 1. It maybe makes sense to you that, again, the density of the air probably matters, air density, because, the density of air tells you how many air molecules there are around the droplet. So as air is moving past it, the density of air tells you, well, how many air molecules are bumping into this droplet, per unit time in the first place. So it again makes sense that, the density of the surrounding air matters, so the density rho, and as we've seen before, this density is going to carry with it dimensions of mass per cubic length, so mass times length to the minus 3. And then if you think hard about it, there's actually one more thing, or at least one more thing, that this force probably depends on, and that's the viscosity of the air. right? So air viscosity, which I'll represent with this symbol, the Greek letter eta. And if we think about like objects moving through or being dragged through a fluid, this kind of makes sense, right? Like imagine dragging something through water, which has a relatively low viscosity, versus dragging something through honey or maple syrup or something like this, which has a higher viscosity, or through peanut butter, which has a really high viscosity. And so, in addition to just how many molecules am I bumping into, something about the viscosity of the substance, which is set by more detailed chemistry, I think it also makes sense that that matters too, right? So we also need to think about another dimensional object, this air viscosity. And this is probably less obvious, so I'll just tell you the dimensions of viscosity. This is a dynamic viscosity. The dimensions of viscosity are measured in mass per unit length, so mass times length to the minus 1 per unit time. So mass, length to the minus 1, time to the minus 1. Okay. And that's great. This is sufficient for us to make progress on our problem. Now, secretly, this problem probably has a little bit of a different feel from the blast problem. Now, remember, what we're trying to do is say, we want to write drag as some combination of all of these things that have the right units, right? So we want to say the drag force, F drag, is equal to some function now of all of these things, a function of the radius, the velocity, the density of air, and the viscosity of air, right? And the dimensional requirement that we're going to have will require, in order to figure out what combination of things we need the dimensions of this force to match the dimensions of this function, right? So the dimensions of capital F for force have to match the dimensions of lowercase f for function, and this function depends on the radius, the velocity, the density, and the viscosity. Okay. Well, what units are involved here? We know that the dimensions of a force, dimensions of force, F drag, that's mass, it's like a mass times an acceleration, so that's like a mass times a length over 2 powers of time. And there's 3 objects here. There's 3 like dimensional things, masses, lengths, and times. And there's also those same 3 quantities in this whole set of units, right? There's lengths everywhere, there's times in a few spots, and there's masses in a few spots. But there's an important difference, right? We have 3 things we're trying to figure out, right? In the same way that we set it up before, where we want to do something like, dimensions of radius to some power times dimensions of velocity to some power times dimensions of density to some power times dimensions of eta to some other power, which I guess I'll go back to w, x, y, z, w. We want, this combination to all be, dimensionally correct. So dimensions of a force. And maybe you see the problem here. We have four exponents that we can play around with here, but we only have 3 things that we're trying to solve for, right? And this makes this problem in some ways very different from the blast problem. There we had 3 equations and 3 unknowns. Here we have 3 things we're trying to figure out. We have 4 equations to work with, right? And what that means is that there's more than one way that we can combine these different things to get something that has the right units, okay? So what's our strategy going to be in this case? It's going to be very similar in spirit to what I wrote, in the other case study. We're going to write F drag. So let me, remove these dimension sign. We're going to write F drag as the product of 2 things. We're going to have something that has all the right dimensions. So we're going to have the right dimensions here, and it's going to be, it's going to be some combination of the things we know are important. And then we're going to multiply it by some other function, f star, which will depend on a pure number, something that's dimensionless. Again, this probably feels a little bit more complicated than the first example, and let's just try to follow along with the logic here. So we know that force has dimensions, and we're going to write that force as a combination of stuff that gives us dimensions of force multiplied by a pure number, in this case, a function of some dimensionless combination of things. Okay. So at this point, there's more than one way to break things down into stuff that has the right dimensions and stuff that's dimensionless. So I'm going to use some of the physical intuition that we will learn about later in this class when we talk about how do fluids behave? Okay, so one, what's a good dimensionless combination to pick, to put inside this function f star, okay? And it turns out that in doing all kinds of problems that involve fluid, and especially fluid flows, there's something called the Reynolds number. Oops. The Reynolds number. It's denoted RE, and it's given by the following combination of these things. It's given by the density of the fluid that something is moving through, its characteristic size, like this radius, the speed with which it's moving through the fluid, all divided by some viscosity. Okay, and you can check for yourself that if you take this combination of density times radius times velocity divided by viscosity, this has no dimensions left over. So it's a dimensionless number, the dimensions of a Reynolds number. It's just a pure number, so I'll say it has dimensions of 1. Okay, so this is one way to combine these 4 items in such a way that it gives you a dimensionless quantity. And a separate way of putting things together to get the right units of force is to combine these in a different way. So again, you can kind of check that. So this is 2. What's a good dimension full combination that has the right units of a force? Well, the next easiest combination of stuff that gives me a force actually only uses 3 of those quantities, and it's the combination a density times a length scale squared times a velocity squared. Okay, so what we can do then is say, so combined, and I apologize, it looks like when I am writing too quickly today, the computer is skipping. What can you do? Combined, what we can say is that the drag force is going to be given by some dimension-full combination, and I'll take this one which, as we'll see later on in the course, or maybe as you think about like a physical intuition of why this is a good combination, takes the density, 2 powers of the radius, and 2 powers of the train's velocity, and it's going to multiply a dimensionless function, right? So lowercase, I'll call it f star, which just depends on the Reynolds number. Okay. Again, from first principles, and certainly at this point in the class, I don't expect that we know anything about what this dimensionless function looks like as you vary the Reynolds number. So it turns out it's something that's been measured. This is a universal function for these kinds of problems, and people have measured it, right? And you can also do a lot of extra work and actually try to theoretically work out what it should be. And so let me tell you that the answer to this is that f star, as a function of Reynolds number, is kind of proportional to the following things. If the Reynolds number is really big, this number is basically just a constant, right? So it's 1, or it's proportional to 1, if the Reynolds number is some big thing, like greater than 100, okay? And it's also basically equal to 1 over the Reynolds number if the Reynolds number is small. For a Reynolds number, let's say less than about 10, okay? So if I were to plot this function, here's the Reynolds number, here's f star as a function of the Reynolds number. For a large Reynolds number, it's basically flat, and then it behaves like 1 over the Reynolds number for small values, and then in between it just kind of smoothly interpolates. This is kind of what this function looks like. That's great. What is the Reynolds number for this problem? Which of these 2 regimes are we in? We can just plug in some numbers that we know. So for instance, we saw in the last example that the density of air, that's about 1.2 kilograms per meter cubed. The viscosity of air, this is probably something nobody has a great intuition for at this point, but for now, let's just say we look it up rather than estimating it. And it's something that's close to 1.5 times 10 to the minus 5 in this reasonable set of units, kilograms divided by meters times seconds, so kilograms per meter per second. And I don't know, let's take a raindrop, which is like, how big is a typical raindrop? Something like half a centimeter. Half a centimeter. Okay, so then what we can do is say, well, great, I know the Reynolds number are, this combination of units, so let's remember the Reynolds number itself is given by the density times the radius times the velocity over eta. So, what is the Reynolds number as a function of how fast the train is going if you just plug these numbers in, right? And it turns out for these numbers, these typical values, what you get is that the Reynolds number is bigger than 100 as long as the velocity of the train is bigger than like 0.25 meters per second. That's really slow, right? Well, it's not really slow, but that's like a train that's just barely starting to chug along, right? It's like less than half a mile per hour, if that kind of set of units is easier for you to think about. So basically, if your vehicle is moving at all, it turns out we're in the regime where this function of a dimensionless number, which does depend on the velocity, actually is in a regime where it doesn't depend on the velocity. It's just gone to a constant. Okay, that makes our life so simple, right? Because a priori, from first principles, I say that word too much, the Reynolds number here depends on the velocity, right? This is rho times r times v over eta. And what we want to know is stuff about the velocity. So if this function really depended on the velocity in the regime we cared about, then our dimensional analysis method would run into a real stumbling block because, the interesting part of the problem appears in a dimensionless part of the final answer, right? But it turns out for reasonable values of, air density, viscosity, droplet size, and also how fast is your vehicle moving, secretly this function doesn't actually depend in detail on how fast the train is moving. It's basically constant. Okay, so that makes our life very easy, comparatively. That means that just by dimensional analysis, we've worked out that for trains moving at any speed and reasonably sized droplets, we have the force of drag being given by, again, some constant, whatever the constant of proportionality is for this function, which again is something that can be measured rather than estimated, if you'd like. So we have some constant multiplied by the dimension-full quantities that are left over, right? Something that has a dimension of force, which again we said would be like rho times r squared times v squared. Okay? So that took us a little while, but we're basically done, right? Going all the way back to where we started this, when we said, scrolling, the tangent of the angle is related to this ratio of forces. Well, we now know how those forces depend on properties of the air, properties of the droplet, and how fast our vehicle is moving, the thing that we wanted to ultimately relate, right? So putting everything together, we have the tangent of that angle has to be given by, the ratio of the force of gravity to the force of drag. We know the force of gravity is the mass of the droplet times the acceleration due to gravity. And we've just worked out that the drag force is like some constant that we don't know, c, multiplied by the density of air times the radius of the droplet times v squared, right? Now, what I wanted was a relationship between angle and velocity. So if I rearrange for the velocity of the train, what that tells me is that the velocity of the train, bringing the subscript back, that's given by the square root of, some big expression. The mass of the droplet times the acceleration due to gravity, divided by some constant that we don't really know, times the density of air, times the radius of the droplet squared, times the tangent of the angle, right? So a bunch of these are some various constants, and, we can do more analysis on this if we want, but let me just simplify a little bit and say, we've got this mass of the droplet, and the mass of the droplet is going to be like the density of water multiplied by 3 powers of the radius of the droplet, right? So the mass of an object, let's say the mass of if I pretend really quickly that, I guess I switch colors for pretending, if I pretend that the droplet is a sphere, the mass of the droplet is like 4/3 times pi times the radius cubed, that's the volume of the droplet, multiplied by the density of the water, right? Whereas this is the density of air, the mass of the water is the volume of water times the density of water. So I can kind of know that there's 3 powers of r hidden in this mass, and there's 2 powers of r down here. So this v train, the velocity of the train, is proportional to the square root of the radius divided by the square root of the tangent of the angle, right? So there you go. We've deduced by dimensional analysis, not knowing very much about the underlying physics of the problem, a relationship between I observe, what angle the droplet is making as it moves across a window, and I can try to figure out how fast that vehicle is moving, right? And this kind of relationship between different quantities is often the sort of thing that dimensional analysis gives you. Rather than like the precise, ooh, I estimate exactly this number, here you can use dimensional analysis to understand relationships between different physical quantities, right? So if I have a droplet that's twice as big and my train is going at the same speed, you can estimate how much does the angle of the droplet have to change as it moves across the window. For instance, that might be something that's fun for you to think about, work out, if r gets twice as big, how much does the tangent of theta have to change to make v the same, because the train hasn't changed its speed? And does that answer make sense when we look at this picture? I see, small drops going at, maybe shallower angles, bigger drops going at slightly bigger angles. What are the relationships between these different quantities, right? Great. It also, this example illustrates one of the shortcomings of dimensional analysis, right? Because we didn't do a full calculation, and that means we were left with a bunch of factors left over that we didn't really know what to do with. We have this number c. We don't know what that number is. It's probably close to 1 because that's like our assumption when we do a dimensional analysis calculation. We don't really know what it is. And in this case, we also had to rely really heavily on what I told you about the behavior of this extra function, right? This function of some dimensionless number. And so often this is the type of thing dimensional analysis gives you back. It tells you what relationships have to be between different physical quantities, but it requires you to still make a measurement of something before you can put numbers down to things. So in this case, in order to know the constants of proportionality, you have to make at least one measurement out in the real world. You know your speed, you measure an angle, you know all of these other things, and then that lets you effectively measure what the value of this constant is. But once you've done that, for the rest of your life, you can know what that constant is and know the relationship between vehicle velocities and droplet trajectories in every other vehicle you ever choose to be in, whether it's a car or a train or a plane. Maybe you'll go on a rocket ship, I don't know, all of these things. So you make a measurement once to determine some unknown properties of your system, and then dimensional analysis tells you everything else you need to know without doing one of these hard calculations. Great. So then I just have a short wrap up in the lecture notes saying, to continue stopping and reflecting about what we've just thought about. We've combined units, which seemed very simple back in section 1.2 or 1.3 or whatever, and together with the idea that physical quantities have dimensions. And then by insisting that different parts of an equation that appear have to have the same dimensions in order for an equation to make sense, we were able to make a huge amount of progress just by inputting some common sense reasoning or understanding about the world around us in order to predict what the relationships between different physical quantities have to be. In this case, speed and droplet trajectory. Sometimes we're even able to predict precise numbers, like in the other case study, the energy of the yield of a nuclear weapon, right? And we did this without knowing anything about aerodynamics or about shock waves or anything like that. We just needed dimensions and some basic physical understanding of the systems that were involved and what things mattered when we thought physically about them. These lists of the drag has to depend on droplet size, velocity, fluid density, and viscosity, things like this, right? Great. So that wraps up this kind of introductory chapter of the course. And in the next chapter, we'll kind of start following along with the How Things Work textbook a little bit more closely. As we do that, think about how this kind of introductory chapter, thinking about units and estimations and dimensions, helps inform your understanding of all of the everyday objects and scenarios that we're going to meet throughout the rest of the course.